Today is talk about why it makes sense in one practical example to measure algorithm complexity in the size of the encoded input rather than the value of the input. So often, when we're learning our runtime analysis, we're always finding complexity of algorithms in the size of the input. Whether that's the size of a bit string or the size of a matrix representation of a graph, whatever. And often, especially for problems where the input is a number, the question comes up, why do we do it that way? Why don't we measure the complexity in terms of the value of the number, this numerical value of the number, rather than the size of the space that it takes to represent that number? So let's take a look. Here is a very, very simple, useless algorithm. It's not even a factorization algorithm. I call it a factor finding algorithm. It just gives you the set of numbers that divide an input number, big N. It says nothing about their multiplicity. It certainly doesn't filter down to only prime factors. So here's the algorithm. You create an empty linked list of true factors that will contain all the true factors at the end. You start at 1. And you march up one by one up until big N, and these are all your list of candidate factors. And for each of those candidate factors, you find the remainder of big N divided by that candidate factor, and if that remainder is 0, you add that candidate factor to the set of true factors, and this can be done in constant time because it's a linked list. And here, this remainder, we're going to abstract away from the implementation of remainder. We'll just say it's an oracle that tells you in constant time what is the remainder when its first input is divided by its second input. Okay, so if you look at this, the algorithm has asymptotic time complexity of theta of big N, where big N is the size of the number. Why? Because we are iterating over a loop. We iterate from 1 to n, so we do this loop n times, and the loop can be done in constant time. Remainder is constant time, and appending can be done in constant time. But if you look at the complexity in terms of the size of the input, it's not theta of big N anymore. It's theta of 2 to the b, where b is the length of the bit string that encodes n. So, what do we mean? So let's suppose that your input is 4. You want to find the set of all factors of 4. So when n, that's terrible. N equals 4, then the bit string is going to be 100. When n equals 5, the bit string will be 101. So you can see here that the bit string is shorter than the size than n. So you could have something like n equals 32, and the bit string is going to be 1,000. We have your 1s, your 2s, your 4s, I'm sorry, that's your 8s, your 16s. It's actually going to be, I'm running out of room there. 1s, 2s, 4s, 8s, 16, 30. Okay, there we go. This bit string is not 32 bits long, clearly. In fact, in general, we're going to call the length of the bit string, we're not going to call it, it is, the length of the bit string b is roughly the logarithm base 2 of n. And so that's where we get this theta of 2 to the b, because this means that n is roughly 2 to the power of b. So if we have an algorithm that is linear time in n, that means it's exponential in b. Okay, so why do we do this? Why do we measure it in terms of this? Why is it more useful to measure in terms of the size of the bit string, and not in terms of the size of the value of big N? And let me give one example. You could say, well, I'm going to get around this by not using a base 2 encoding. I'm going to use a simple encoding. I don't call this base 1 because I have this is not true base 1. True base 1 is an impractical way of representing numbers. It would take an infinite amount of space to represent any number, but people call this base 1. They just say, okay, when n equals 4, my base 1 represents... It's terrible. When n equals 4, my base 1 representation is going to be 1, 1, 1, 1. So that's 4 tally marks. When n equals 32, my base 1 representation is going to be 1, 1, 1, until I have 32 tally marks. So then it really is. And then you say, okay, the size of my input is exactly equal to the numerical value of my input, so I've gotten around this problem. Now I can say that I have an algorithm that runs in time linear of the size of its input. And so why is this not useful? Why is there a better way of representing this? And the reason is that we have a more efficient representation of this number rather than this tally mark representation. We have the base 2 representation. And you can see this in particular when you look at problems of cryptography. You want the encryption to be cheap because you want to use the encryption, but you want the decryption to be cheap also, by the way, if you have the secret key in the case of asymmetric encryption, or even symmetric encryption. But you don't want breaking the encryption to be cheap if you don't have the secret key. If some eavesdropper doesn't have the secret key, you don't want them to be able to break the encryption cheaply. And that's exactly what something like this does, is that if you have an efficient way of representing input, let's suppose that the trapdoor function here that underlie our encryption problem is the problem that I just mentioned. Find the set of all factors. You can encode the number that you are setting as the challenge. You can encode the number with space that is only your space b is going to be log 2 of the number n. And when they try to factor it, when the eavesdropper tries to factor your number, they're not going to be spending log of n space. They're not going to be spending linear in b space. They're going to be spending, like we saw, 2 to the b space. Okay, so what is the practical implication of this? Okay, let's suppose, and I'm just making up these numbers, they're not reasonable, but let's suppose that space costs $10 a bit. So we say space, this is horrible. Oh, dope. All right, that's okay. You guys remember what it says. Okay. Whoops. Space is $10 per bit, and time is $1. $1 per CPU cycle. Okay. So when you encode your input, you are going to use 10 times the number of bits you use. That's the cost to you. But when the eavesdropper tries to crack your encryption, they're going to use $1 per cycle. Okay, so let's suppose that we use 1 bit. Let's suppose we use 1 bit. With 1 bit you can represent 0 or 1. That's the numbers you can represent. 1 bit, it's going to cost us $10 to encrypt this, to store the challenge, and it will take them 2 to the b, which b here is 1. It's going to take them 2 to that power of cycles to run this. So it'll take them 2 times $1, which is $2. This is not a very good dollar sign. You guys know what it is. Okay, so this looks like a horrible deal. This is like a horrible deal. Wow, you know why I'm spending $10 to encode this. That's what it takes me to use this encryption, and somebody can crack it for $2. This doesn't look like a very good trade-off. Okay, let's apply this to 2 bits. With 2 bits, we're going to pay $20, and we can get up to the number 4, which means that they're going to need $4. Okay, so $20 versus $4 doesn't look like a good deal. With 4 bits, we're spending $40, and we can get up to the number 16. We'll get up to number 16. And they, for that reason, are going to be spending up to $16, you know, asymptotically in the order of $16 to solve this problem, if they use the naive algorithm that I was telling you about. Okay, so now let's look at what happens with 6 bits. Okay, so this was 1. No, it doesn't want to work for me. 1 bit. So now let's look at 6 bits. It's a really bad 6. With 6 bits, you're paying $60. But you can represent with 6 bits up to 2 to the 6, which is 64. So asymptotically, they will spend $64 to crack your encryption, which costs you $60 to store the challenge. Okay, so now this is looking like roughly, you know, this is breaking even. It costs you roughly as much as it costs them to crack it. Still doesn't look like the best deal, but you're starting to see the pattern here. Okay, so now let's think about 32 bits. Now let's think about 32 bits. 32 bits. You're going to spend 32 times 10. Each bit we know is $10. You're going to spend $320 to store the challenge. And they will spend asymptotically on the order of 2 to the 32 dollars to solve it, which is more than $4 billion. So you're spending $320. You're spending $320 to store this challenge, and they're spending over $4 billion to crack your encryption asymptotically. You know, they could get lucky and guess, but in general, in the worst case, they're going to be spending up to $4 billion on that order. So now you can see what is the problem. We started out with something that looked like it greatly favored the eavesdropper. You know, their CPU cycles are a tenth as expensive as our space. Our space is 10 times more expensive per unit than their CPU cycles. But because we have an efficient encoding, we can store up to this very, very large number, you know, over 4 billion. It takes us 32 bits at most to store this because of our efficient encoding. And it's going to take them a lot more time to crack that, to solve the problem. And so if we had used the, so this is the practicals, right? In the real world, if you had used that old base 1 representation that disappeared now, which is fine because I wouldn't have had space anyway, that old tally mark representation, you know, if you want to represent 4 billion, you have 4 billion tally marks and you're spending $40 billion to encode this, and they're only spending $4 billion to crack it. But that's not the point here. This is not just some theoretical exercise. It just has some practical interpretation. And in this case, the practical interpretation is that because you have an efficient encoding of this input, you can store the challenge quite cheaply in the asymptotic case, and but it takes a long time to crack that challenge. So this is just an example of, in the real world, why would you want to measure time complexity in terms of the size of your encoded input? And you know, this includes, you know, you can represent a graph as a matrix. You know, a graph with n nodes, you can represent it as a matrix of n by n matrix, where, you know, you have zeros if there's no link, and 1 if there is a link between two nodes. Or you could represent it as a list, a dictionary. Okay, you have the nodes as the keys, and you have their neighbors as the values, a list of neighbors as the values. These two different encodings, the same algorithm could have slightly different runtimes on these two different encodings depending on how efficient it is to convert between one and the other. If you have a very simple algorithm that is something that requires constant lookup versus iterating over a dictionary, you can in an array you can just hash right into the element that you're interested in if you know the element. With a dictionary, maybe you can't hash right in because you have the dictionary is kind of it's not laid out sequentially. It's not the memory isn't laid out contiguously, so you can't maybe hash right in, but maybe it's much easier. You don't have to iterate over all n. You don't have to iterate over all n nodes. You can just get to the list of nodes directly or whatever. But the point is that you want to measure the complexity of an algorithm with respect to the size of the encoded input in practical terms. And this will give you a much better understanding of how expensive is it to solve the challenge versus encode the challenge.